My name is Michael Lee. I am a Technology Development Project Manager on the SoCalGas Research Development and Demonstration Team, or RD&D. For today's webinar, we will be welcoming Dr. Mark Allendorf and Dr. Vitaly Stavila from Sandia National Laboratory to discuss materials-based hydrogen storage for heavy-duty vehicles. Before we begin, I'd like to walk everyone through the GoToWebinar toolbar that should be visible to all attendees. Please enter any questions in the questions box, and we'll review these during the Q&A session after the presentation. During the Q&A session, we will also open up the discussion for verbal questions. If you'd like to speak, click the raise hand icon to be called on during the Q&A session. When you are called on to ask a question, we will first grant you access to unmute. Then you must manually unmute yourself. After you've given your question, please go back on mute after asking a question. And finally, you will find a few valuable documents in the handout box. Now a comment on SoCalGas's commitment to diversity. SoCalGas is dedicated to improving the quality of life in the diverse communities we serve. To support this commitment, SoCalGas RD&D staff conduct outreach efforts and activities to engage with disadvantaged and underrepresented groups throughout California, notify researchers, entrepreneurs, and businesses about RD&D program funding opportunities, share the results from RD&D projects to inform and educate the general public. Today's webinar is just one of the ways we do this. And lastly, track and report progress in diversity outreach efforts in our annual report. The SoCalGas RD&D program is divided into 5 areas that span the entire energy supply chain, from low carbon resources, where we look at renewable gas production, carbon capture, utilization, and sequestration, to gas operations, looking at distribution, environmental safety, operations, technology, system design, and how we use these gases or fuels through clean transportation, clean generation, and customer end-use application. In 2020, the SoCalGas RD&D team managed 386 active research projects. On average, RD&D projects generate a 6.9 times funding ratio, meaning for every dollar of RD&D funding provided to a project, the project also receives nearly $7 of external co-funding. More details on the RD&D program are available in the 2020 annual report, which is included in your handouts today. This year, we produced a Spanish version of the annual report as well to better connect with the diverse communities in our service territory, also included in the handouts. I'd also like to share with you an upcoming webinar on November 4th. We will host UC Irvine to discuss a DOE-supported project looking at decarbonizing steel production with green hydrogen. So stay tuned for that. And we'll send out some of the save the dates and meeting information after this presentation. And finally, we want to stay connected with you, our stakeholders in the research community, and the general public. Please visit our website where you can find our annual report, information about our upcoming webinars, and news about the RD&D program. And please reach out to the RD&D team via email with questions, comments, or research suggestions. We also maintain an RD&D page on LinkedIn and on the CEC's research networking platform, Empower Innovation. Before I pass it over to Mark and Dr. Mark Allendorf and Vitaly Stavila, I'll give a quick introduction to them. Dr. Mark Allendorf is co-director of the DOE Hydrogen Materials Advanced Research Consortium, also known as HyMARC, and a senior scientist at Sandia National Laboratories in Livermore, California. A principal theme of his research is the development of solid-state materials for efficient hydrogen storage. In addition, he has led projects on chemical and radiation sensing, electronic devices, and catalysts for biofuels production. His research has generated more than 200 publications, as well as 13 patents. He is past president and a fellow of the Electrochemical Society and has received Sandia Awards for research, leadership, and teamwork, as well as a 2014 R&D 100 award. Dr. Vitaly Stavila is a task lead in the DOE HyMARC. In his current research, he uses various X-ray scattering and diffraction techniques to solve fundamental and applied material science problems related to bulk and nanostructured metal hydrides, oxides, and metal organic frameworks. A central theme in Dr. Savila's research is the rational design of new materials by changing the chemical composition, the arrangement of the atoms or molecules in crystalline or amorphous configurations, and the size, shape, and orientation of nanoparticles, crystals, or other nano or macroscopic units. Now, without further ado, I want to welcome Dr. Mark Allendorf and Dr. Billy from Sandia National Labs. Mark and Billy, I'm excited to hear about your research on materials-based hydrogen storage for heavy duties. I will transfer presenter mode to you. So welcome.
Is my screen visible now?
It is.
Okay, great. Well, hello, everybody. Thanks so much for joining this webinar. I'm really pleased to be able to tell you about the research that we're doing, sponsored by SoCalGas, as well as the Department of Energy. Before I start, I want to just thank my team, Austin Acosta, Robert Horton, Vidley Stavila, Joe Reynolds, John Snyder, and Matt Whitman, who have contributed, in fact, done the research here. I'm just making the presentation. So let me give you a little bit of an overview about hydrogen. So in the last couple of years, the interest in hydrogen across the board has really skyrocketed. A few years ago, the DOE started something called H2 at Scale, which was an effort, or is an effort, to take a comprehensive look at a all hydrogen economy, which ranges from the production of hydrogen, its use for generating electricity, as well as in various forms as a fuel. Now, when I started my research in hydrogen storage about 15 years ago, really almost everything was focused on storage for vehicles, onboard storage for vehicles. And that was because vehicles contributed such a large amount of greenhouse gases. So a lot of work was done on that. But since that time, we've really begun to expand our view of the hydrogen economy beyond light-duty vehicles to include not only the storage on board, but also the transport of hydrogen from wherever it's produced to a delivery point. We've also started thinking about how hydrogen is used to make synthetic fuels, and therefore the way that you make hydrogen. Can it be done in a green way, that is without producing greenhouse gases? And also the viewpoint in terms of transportation has expanded dramatically to include not only heavy duty vehicles, but things like rail and ports. So it's a very vigorous area. And you might be aware that just about a month and a half ago, the Biden administration announced its first Earthshot, which is focused on the production of hydrogen. The goal here is to produce hydrogen for $1 per kilogram and achieve that within 1 decade. And I can say that's a very ambitious goal. Just to calibrate you, a kilogram of hydrogen is roughly the equivalent of a gallon of gasoline. So $1 a gallon would be the production cost. And then, of course, one does have to add on costs associated with delivery and the associated infrastructure. So I'm going to back up a little bit and just tell you how we got to this point. The DOE, back in about 2009, defined a set of targets for onboard storage of hydrogen on light-duty vehicles. In fact, you can see a commercial car up there in the upper left. That's a Toyota Mirai. And these cars, they store hydrogen as a gas at high pressure, about 700 bar. And they do it in specialized fiber-reinforced tanks. And there's a lot of issues with these, cost being a major one. But if we just compare them with what can be achieved or what should be achieved in the DOE targets, what you find is that it's not possible to meet the DOE volumetric capacity target at 700 bar. It's physically impossible. So this has motivated for some time some substantial research efforts around the world to develop materials-based solutions to store hydrogen on board. Now, this has evolved, as I said, and a couple of years ago, the DOE published a new set of targets focused on heavy-duty vehicles. And the objective here is to try to get competitive technology on the road, possibly as early as 2030, to, of course, inform and guide R&D activities and provide guidance to manufacturers for fuel cells and storage and infrastructure, all these components that contribute to the use of hydrogen on board a heavy-duty truck. I just mentioned here that SoCalGas is a project with Toyota Kenworth, where they've manufactured about 10 fuel cell Class 8 trucks for drayage and are testing these now. So among the targets, there's about a dozen of them, but the 4 that are shown here are the ones that focus specifically on sort of materials-related aspects. So first of all, the hydrogen fill rate, there's a target for that of 8 kilograms of hydrogen per minute, ultimately going up to 10. The one at the bottom, hydrogen storage system cost, that's a little bit less directly related to the material, but the things that contributed to it are, of course, the cost of the storage material and the cost of the tank and associated infrastructure. So these are the 2 targets that are really most closely linked with the SoCalGas project that we have, as well as the research that we're doing under the funding of the Department of Energy. So to orient you a little bit, there's a number of ways that you can store hydrogen. The physical basis, a physical way to do it is simply to use it as a liquid, so at cryogenic temperatures, or as a compressed gas, as I mentioned. And then there's a kind of in-between, a cold cryo-compressed strategy that's being investigated by some automakers. But then we have a number of materials-based possibilities that range from adsorbents. So these are nanoscale materials, very small pores that bind hydrogen rather weakly, but they have such huge surface area that they can store quite a bit of gas. Then going all the way to the other end of metal hydrides, complex hydrides or chemical hydrogen, where you have actually a chemical compound to where hydrogen is bound to either a metal or some main group atom like aluminum or boron. So there's a whole spectrum here. Right in the middle are so-called interstitial hydrides, which could be ideal, except that they're very heavy. They can store a lot of hydrogen on a volumetric basis, and you can desorb the hydrogen and load it on very quickly. But when you compare that to their gravimetric capacity, they're really not suitable for most transportation applications. However, some of these are being used in equipment delivery. So for example, forklifts, there's something like 30,000 hydrogen fuel cell powered forklifts in this country, and they use interstitial hydrides to store the hydrogen. So it's useful, I think, to kind of put this in perspective. How does hydrogen compare with other fuels? 2 key metrics that we use are the gravimetric capacity and the volumetric capacity. So the gravimetric capacity is either the power or the mass of hydrogen that is stored per unit mass of the storage material. And similarly, the volumetric capacity is power or mass per unit volume. Now, these are material-based targets. In other words, you look at the material itself and you simply compute how much hydrogen there is in it. But if you look at the DOE targets for onboard storage, these are system targets. And what that means is they're targeting a certain amount of hydrogen to be stored in the entire fuel cells, or entire storage system, so the tank, the associated cooling tubes, everything else that goes into that. And so, to calibrate on that, it's often the case that people estimate that balance of plant by just a factor of 2. So for example, if you had 10 weight percent storage capacity and a material, it's system capacity would probably be something more like around 5 weight percent. Now, this graph here shows conventional hydrocarbon fuels in terms of their volumetric and gravimetric density, and compares it to pure hydrogen, which is shown in the block, the green block down at the bottom. And you could see that hydrogen outstrips all of the hydrocarbons in terms of its gravimetric density, but it's very low when it compares with the volumetric density. So this is really the crucial problem that is focused on by much hydrogen storage research. I think it's important to point out, though, that if you were to compute the hydrogen capacity of these hydrocarbons, so in other words, just strip the hydrogen off of them and burn that, as opposed to burning the entire fuel to make CO2 and water. If you did that, the capacities of these would drop quite a bit, by a factor of 2 or 3. So hydrogen is actually very competitive relative to other fuels when it comes to the amount of hydrogen present in a given mass or volume. Now, there's dozens, if not hundreds, of different materials that have been looked at over the years for storing hydrogen. So I'll give you a little bit of an overview of these. This is a chart that shows the hydrogen capacity in terms of weight percent on the vertical axis, and the temperature at which it is either has to be stored or the temperature to which it has to be heated to be released. And if we look at sorbent materials, so again, these are nanoporous materials, these can store a lot of hydrogen, but you have to cool them down to cryogenic temperatures. So you see that the highest capacities in this block here are materials that are stored at like liquid nitrogen temperature. And what that is caused by is that the hydrogen interaction with these pore surfaces is very weak, maximum of about 10 kilojoules per mole. So the only way that you can get a lot of hydrogen to stay on there is to cool the material. Alternatively, the other big class of storage materials are metal hydrides. And these materials can also achieve rather high gravimetric capacities, but they suffer from exactly the opposite problem from sorbents. In this case, the hydrogen is bound much more strongly to another element, which means that you have to heat it in order to drive the hydrogen off. And the amount of heat depends on the strength of those bonds. There are metal hydrides where you can heat them to 100 C or less. Others require much more. The consequence of that is that if you were doing this on board a vehicle, you might have to burn some of the hydrogen to get the fuel bed up to a temperature where it would release its hydrogen at a rate that would be usable for the fuel cell. Now, this red box shows you the DOE targets, and there are several of them at different years. An ultimate target being the highest capacity that we can achieve. The important point to note here is that there aren't any symbols in there right now, and that's because hydrogen storage is in what I like to call a sort of chemical no man's land. The materials either bind it too weakly or too strongly, and we need something that's exactly right. It's sort of a Goldilocks problem. So that's why very much of hydrogen storage research has focused on things like the weight percent and the temperature at which the material is released. What I'm going to show you is that we've realized that we have to take really a broader view and strategy towards developing new storage materials. We have to take into account actually the entire fuel system, because there's other elements of it that contribute to how much hydrogen in the tank is actually accessible. So you might have a lot of hydrogen in there, but for example, if you store hydrogen even as a pressurized gas, you have to provide at least 5 bar of hydrogen pressure to drive the fuel cell. So any hydrogen in the tank that's there at pressure below 5 bar is unusable. And that applies to sorbents and other materials as well. So this is really a major challenge, and it has been, as I said, a focus of research for a number of years. And about 6 or 7 years ago, the DOE convened a workshop of storage experts and asked, why is it that we have not been able to develop a successful material up until now? And the consensus was that there are some fundamental technical issues that we really don't understand, and until we actually solve those, we're not really going to be able to do more than a sort of Edisonian approach of trying different materials until we find one that works. So in 2016, they started HyMARC, which is a team of national laboratories. So this is what's called an energy materials network. There's a number of these. There's one called LightMat that focuses on alloys for lightweight alloys for vehicles, electric catalysts for fuel cells, and so on. HyMARC is focused on storage, and in our first phase, which was basically 2016 to 2018, we only had 3 national labs. There were 3 in the Bay Area: Sandia, Lawrence Livermore, and Lawrence Berkeley. And we were very focused on some foundational R&D to address these questions of what is blocking the discovery of successful materials. After those 3 years, we actually expanded. We went into a second phase, a 4-year phase, where we brought in 2 other labs, Pacific Northwest and National Renewable Energy Lab in Golden. And these 5 laboratories collaborate in a very horizontal way. And we also make use of a number of DOE and other user facilities, such as the Advanced Light Source at Lawrence Berkeley Lab. And we use these cutting-edge tools to really get in and understand how these materials are behaving, what their structure is, and what's occurring to them when they actually undergo decomposition or reabsorb hydrogen. So we're now in this second phase of HyMARC, and what we've learned here is allowing us to take a look at storing hydrogen on a Class 8 vehicle, which is the project we have with SoCalGas. Now, everything I've talked about up until now in terms of hydrogen capacities and materials has really been on bulk materials, specifically bulk metal hydrides. And bulk metal hydrides, at least on paper, have the highest capacity, but one of the things that limits them often is their thermodynamics, as well as the rate at which they release hydrogen. So it's been learned through a lot of research that HyMARC has done, but also others, that if you scale down the critical dimension of a metal hydride to something like a few nanometers, and this is a little bit of a vague area, it could be a few nanometers up to 10, 20, it's not really been nailed down that clearly. But if you do that, there's tons of evidence that shows that you will destabilize the material and it will release its hydrogen at lower temperature. So this actually has become a principal strategy of HyMARC to apply to metal hydrides that, for one reason or another, don't work in the bulk phase. But if you put them, for example, into a porous carbon host, something with pores, let's say, that have diameters of around 5 to 10 nanometers, that what you do is you can improve both the thermodynamics and the kinetics in some cases. That's sometimes due to reduced diffusion lengths, but it also is destabilizing it because you're increasing the surface to volume ratio. And these porous hosts also serve to prevent agglomeration. They provide a pathway for heat transfer. And you can actually tailor the pore with different elements or groups that can further promote the reactivity of the hydride. If you're interested in a sort of up-to-date summary of what's going on in this field, you can look at that research article that I mentioned at the bottom there, which we published a couple of years ago in Chemical Reviews. Now, this slide here gives you a little bit of a demonstration of how significant this nanoscaling effect can be. Lithium amide is an attractive hydrogen storage material, but its enthalpy of desorption, that is the heat required to desorb hydrogen for the bulk material, is about 67 kilojoules per mole, which you see in that plot in the lower left. If we infiltrate a porous carbon that has pores about 6 nanometers, we find that we can reduce that by over 20 kilojoules per mole to about 45. And that's a huge effect. That's enough to drop the temperature of onset of hydrogen release by several hundred degrees. And interestingly, we find that this material is very stable. We can cycle it at 250 degrees C. So in other words, you heat it up, it releases hydrogen, then you repressurize it. In this case, it's about 100 bar, and you can regenerate it. So this is a cyclable, renewable material for storing hydrogen. And an important point here is that you're storing it not only in a bulk form, but at pressures a factor of 7 lower than you would have to use if you were using pure gas, pressurized gas. And that's a big deal because the compressors and infrastructure required to build a fueling station for 700 bar is substantial. It's quite expensive. Now, I mentioned a little bit earlier that we're trying to take a more comprehensive view in this materials discovery process. And this slide here illustrates how we're doing this. And it also dramatically shows how a nanoscale material actually can be better than a bulk material. So what we're doing here is a system model where we input some design parameters for a tank. So its weight, the number of cooling tubes, its size, and the nature of the storage material. And then that's fed into another code. It's called the framework code that will do a real-time simulation of the operation of a fuel cell. And it will predict the temperature in the tank. It will predict the rate at which the hydrogen is released in real time. And you do this with a realistic drive cycle. So the one that's shown here is called USO6, and it's a fairly standard drive cycle for light-duty vehicles, and actually a fairly strenuous one. And what we have to do to get to this point is experiments that provide the hydride loading. This was a lithium nitride material that it's hydrogenated to make a lithium amide, and it's in a porous carbon. We provide the loading there. We provide the thermodynamics and kinetics of that material, its thermal conductivity, and the packing density. And what we find is if you take that information for the bulk material and put it into the framework model, you can't even start the fuel cell. And the reason for that is that the hydrogen, heat that is required to drive the hydrogen off, there's too much of it is needed. You can't heat the bed up uniformly and generate enough hydrogen at the rate needed to run the fuel cell. So the thing just doesn't even start. Alternatively, if you take the nanoscale material has a much higher thermal conductivity because the hydride is trapped inside of the pores of this carbon. And the porous carbon essentially is graphite, which is a very high thermal conductivity. And what we find under those circumstances is that we can start the fuel cell and it will run at a stable pressure of 55 bar, assuming a operating temperature of 250 degrees C. So right away, what this tells us is just looking at the simple arithmetic of how much hydrogen is in a material is not enough. You have to look at take a more comprehensive view of how the hydrogen interacts with the entire system. So 250 degrees is a bit high. We would much prefer to have that lower. I mean, the optimal would be if you could run this at 80 degrees C, and then you could use the residual heat from the fuel cell. That's really challenging. There's only a couple of materials that will do that, and they don't have the capacity that is required to meet the DOE target. So our strategy in this Southern California gas project is to ask the question, could we use a nanoscale metal hydride, or at least a form of a metal hydride that has much higher thermal conductivity, and be able to run it at a temperature of 200 C or lower. And if we can do that, we should be able to switch from heavy stainless steel tanks to lighter tanks that are made out of aluminum alloys, for example. And we would also be able to abandon the very expensive fiber reinforced composite tanks that are currently in use now for pressurized gas. So the objective, therefore, of the SoCalGas project is to evaluate a very specific metal hydride in a nanoscale form. We call these composites, and we'll generate the information that's needed to simulate a heavy-duty vehicle. So we will have a version of these systems codes that is designed to simulate a heavy-duty vehicle, not a light-duty passenger vehicle. So our strategy from a materials point of view is to do basically four things. We need to reduce the thermodynamics, that is the heat required to desorb hydrogen, to a value that is low enough that will allow us to operate at these lower temperatures. We need to improve the heat transport, that is the thermal conductivity, so that we can get heat in and out of this bed and drive off the hydrogen or regenerate the material. We need a capacity above a mass fraction of 4%. And we need to have kinetics that are fast enough that, again, we could drive the hydrogen release at less than 200 degrees C. So you can see in the red in this table, these are the values that we're targeting. And if you go further down, you'll see some of the materials that we originally looked at in HyMARC. For example, the bulk lithium nitride with a little bit of potassium hydride doped in there to improve the kinetics. Obviously, the enthalpy of desorption there is way off from what we want. If you put that into a 3 nanometer porous carbon host, you have a big drop of about 20 kilojoules per mole. And simultaneously, you have a factor of 4 increase in the thermal conductivity. If you broaden those pores, make them bigger up to 6 nanometers, you have a little bit further improvement in the enthalpy, and you maintain that attractive high thermal conductivity. So that's probably about the limit that we can go to with the lithium nitride, lithium amide system. So our strategy here in this project is to look at a compositionally tuned version of that, where we substitute some of the lithium with magnesium. And we basically call this a 2-to-1 material. It's 2 moles of a lithium amide and magnesium hydride, and when those react, they turn basically into a mixture of lithium hydride and magnesium amide. And the bulk material there has very good thermodynamics. It's right where we want it to be. But as typical for bulk materials, the thermal conductivity is poor. It's less than a watt per meter Kelvin. Capacity is good. And the operating temperature should be pretty attractive. We can desorb over 75% of this material's hydrogen at 180 degrees C. So this is promising if we can increase the thermal conductivity, and we also need to work on improving the kinetics of release. So if you're not familiar with metal hydrides, this is just a little slide to show you in a sort of tangible way what they are. These are not exotic materials. They're used extensively, not just to store hydrogen. They're used in batteries. In fact, a lot of laptops actually have nickel hydride batteries in them. That's probably the biggest use of metal hydrides in the world. But they're commonly available chemicals. You can make different forms of them in very simple ways. We use a ball mill, for example, where you just put the powder in and you shake the heck out of it to mix it very thoroughly. You can use that to tailor its the size of the particles as well. So these are not intrinsically exotic or high-cost materials. Now, one of the most important things we measure is the thermodynamic properties, and we do that using something called a Sievert's apparatus, which is shown schematically on the left there. Basically, what you do is you put a sample of your hydride in there, and you heat it a little bit and desorb some of the hydrogen into a calibrated volume, and you keep doing that, and eventually you get to a point where you reach a plateau, and that's the equilibrium pressure of hydrogen above the material at a specific temperature. And when you do that, you can do that as a function of temperature, and that gives you data that you feed into something called the Van 't Hoff equation, shown down there in the lower right, and from that data, you can extract both the enthalpy and the entropy. So knowing those two numbers allows you to predict the pressure of hydrogen above a material as a function of temperature. And that's absolutely a critical engineering number to know. Now, we're also measuring the thermal conductivity, and the way we do that is we take powders of these hydrides and we press them into discs at about 10,000 psi in a glove box, and then we put that on a little nickel coil, or sandwich it in around a nickel coil, and when you heat that, you get a change in the heat release of the material, and you measure that, and that slope is related to the thermal conductivity. The data that I show here on the right illustrates just this dramatic effect of nanoscaling. You can see that all of these three bulk materials are around 0.7 or so to about 1, and it's pretty stable with temperature. But if you nanoscale it, the thermal conductivity shoots up by a factor of at least 3.5. So this is really a dramatic effect. So we started modeling that and studying that more carefully, and done things like take a very simple solution. Rather than infiltrate a porous material, let's just take a strategy where we take something like expanded natural graphite. It's just a form of graphite. And you mix that in some quantity with the metal hydride and measure its thermal conductivity. And what you can see is over here on the left, you got values at 2 different temperatures for the bulk material without any carbon in it. If you add just a little bit of carbon to it, it doesn't really have much of an effect. It looks like it drops, but I think it's probably within the experimental error. However, if you put about 10 weight percent in there, you get quite a substantial increase. And in fact, if you're willing to play with both the amount and the temperature, you can increase the thermal conductivity of this hydride by about a factor of 3. So that gets us to the value that we need in order to drive hydrogen off of the hydride at a rate to run the fuel cell. You might be wondering how you would make a nanoscale material. So for the chemists in the audience, I put this slide up there. There's several ways of doing it. The one that we've adopted, at least initially, is something called incipient wetness impregnation. And basically what you do is you take some precursors to the lithium and magnesium, you put them in a solvent and submerge the porous carbon in that, and these nanopores will wick in the solution and fill up, and then you can react that with hydrogen, or you can react it with hydrogen and ammonia, a couple of different reaction schemes that are shown there, and generate the lithium magnesium amide, or if you drive off the hydrogen, you can get an amide. So that's the basic reaction that occurs. Down below there, you can see powder X-ray data. X-ray diffraction is really the main tool that we use to verify that we have created a metal hydride with a certain structure. These porous carbon hosts are also not particularly exotic. If you're not familiar with them, you've probably heard of something called activated carbon. Activated carbon is used widely as a filter of organic material, like in water, for example. So if you've got a refrigerator that delivers water, it almost certainly has a water filter in it that's filled with porous carbon. And this stuff can be made from a lot of different materials, even peanut shells. And of course, there are fancier ones that we've worked with where we try to get a higher pore volume per gram of the material so that we can get more hydride in there. But the uses are broad. We're obviously in a very research-oriented program, but water purification, as I said, is an application, and they're used in electronics, cosmetics, and gas storage. So the point is, the raw materials for hydrogen storage are readily available, not exotic, and should not be expensive if manufactured on a mass scale. Now, in this last little bit of the talk, I want to tell you about the modeling that we're doing. So I mentioned some of this in an earlier slide, this tank modeling that we're doing, and this is kind of the final step of our project with Southern California Gas, is to take the experimental data that we've obtained for these lithium amide materials, nanoscale materials, put that into these codes. There's two codes. One of them is called the Tankinator code, and this is used to basically design the properties of the storage system, the tank size and the amount of cooling and various other infrastructure aspects. This code requires a couple of key inputs, the thermodynamics, as I'm showing up there, the enthalpy and entropy of reaction, and the thermal conductivity, along with some other things. You run that code, and then that outputs the system capacity, mass, and volume, and some information about the system size, and then you put that into the framework model. And the framework model adds one extra dimension, which is the kinetics of the hydrogen release. So the strategy here is to design this tank based on the materials that we're looking at, put that in a framework model with kinetics, and then run the framework model and ask the question, does the car complete a drive cycle? So that's the strategy. Now, what I'm showing here are Tankinator calculations that we've run to get a handle on where we stand with our materials in terms of the targets that we have for the thermodynamics and the capacity and the heat transport. So what you see on that upper left-hand 3D plot there, that is a plot of whether or not a specific combination of properties either meets a target, and in this case, the target is to meet or exceed the volumetric capacity of 700 bar hydrogen gas. So if the little dot is yellow, it meets the target. If it's blue, it does not. And the 3D shows that for different hydrogen capacities, for the enthalpy, that's delta H, and the entropy, delta S. And then we do that, so that three-dimensional calculation is expanded to include the density, so that's over here on the right, in the horizontal axis, rho, kilograms per cubic meter, and the heat thermal conductivity, kappa, on the vertical axis. So you can see here that there was actually thousands of calculations that were done to map out this parameter space. We actually automated the Tankinator code so that this could be done quickly. What you see is that sort of the canonical baseline material, this potassium doped lithium nitride, this little red star up there. You can see that its density and its heat capacity are both too low to meet the target. And similarly, if you were to put that into the 6 nanometer porous carbon, you make a huge increase and improvement in the thermal conductivity, but you're still not where you need to be in terms of the loading, and really more specifically, it's the thermodynamics that are limiting things here. Alternatively, if you look at this 2-to-1 lithium magnesium material that we're focusing on now, you can see we've been able to get a much higher usable capacity out of that. That's the purple star. It still doesn't have good heat transfer properties, but we hypothesized that we should be able to improve that by enhancing it with either the nanoscaling or mixing it with a nanoscale high thermal conductivity material. And that's what the blue arrow is showing. That's our target, and we're actually getting pretty close to that right now with a couple of different strategies that we're looking at. So these are not the framework calculations yet. We don't know what the behavior of the fuel cell will be like, but certainly the properties of the tank based on this material are looking very promising. We also want to look at different tank construction materials. So as I mentioned, 316 stainless is certainly standard. It's what's used to make pressurized gas cylinders for hydrogen. And what I'm showing in a couple of these tables here, I'll guide you through it. this is the gravimetric and volumetric capacity, the percent of what you would have at 700 bar. And this is assuming an operating pressure of 100 bar. So there's a whole bunch of alloys along here. Here's 316 stainless. And what you see is that it does okay on the volumetric side, but it's really lousy on the gravimetric side. And that's just because it's so heavy. Alternatively, we can make a pretty darn good improvement in the gravimetric capacity, and we can improve the volumetric if we go to this A286 alloy. This is actually a steel, not an aluminum alloy, I believe. Even better, if we could drop this pressure to 50 bar. So in other words, operate under conditions where the thermodynamics and the kinetics are good enough that you don't need to heat it so much, you don't need so much high pressure to drive the reaction. Then we can make even bigger improvements. So everything does improve under those circumstances, but you'll see that the best is still this A286 alloy. So what we're getting out of this is some guidelines into the kinds of materials we would want to choose to fabricate a tank. Now, I'm not a metallurgist, I'm a chemist. So if we got to this point, the next step would be to turn this over to people who know how to design these tanks, and they would be able to assess the appropriateness of a given alloy to operate at a certain temperature, pressure, look at things like hydrogen embrittlement. So there's a lot that goes into it that's beyond the storage material itself. Now, sort of the logical question is, well, if you're successful in this project, then what might happen? Well, we can draw a line between what we're doing right now and something that would look like a prototype tank. And Sandia has actually done this before. About a decade ago, we had a partnership with GM where they actually constructed a full-scale tank that stored hydrogen in the form of a metal hydride. In this case, it's something called sodium aluminum hydride. And they mixed it with a little bit of expanded natural graphite to improve the thermal conductivity, which is the basis of our strategy for the lithium and magnesium system. And they had all the other infrastructure that's in there to run or simulate a fuel cell. They didn't actually have a fuel cell on there. But this is a significant amount of metal hydride. Each one of these modules holds, I think, about 1.5 kilograms of sodium aluminum hydride. So the entire tank system had almost 22 kilograms of storage material. So we have experience doing this. If we can arrive at a material that we think is going to be successful, then our next step will be actually to scale up the synthesis of that. You know, we typically work with quantities of a few grams. I mean, this is a research project. It's low TRL. But a next step to raise that technical readiness level would be to synthesize larger quantities and simulate on a very small scale what a storage tank might look like. And eventually that provides the engineering information that you need to design a full-scale system like this. So I'm just going to leave you with a few take-home messages here. And in fact, I'm just going to read them because I think I'm at my time or very near, and I want to leave time for people to ask questions. And I also want to thank the sponsors, SoCalGas, for supporting this research, as well as the DOE, which has been really marvelously supportive for us over the last 6 years, and we're looking forward to continuing that work. So with that, I'll finish. Thank you very much for your attention, and I hope it's been educational.
Thanks, Mark. That was definitely informative and exciting. I want to open up this time. I think we have about 10 minutes left, but we can always extend if there's more questions. But I want to open up this time for Q&A. Now, a reminder, if you have a question, click the raise hand icon, and we will call on you during this session. And you can go ahead and unmute yourself, and we'll grant you that access for you to ask your question. But if you don't want to ask your question, feel free to type it into the chat box or the question box, and we will go ahead and ask the question for you. So, Mark, I do have one question here from McGregory. It's what do you think drives the change in enthalpy of binding when you go to nanoscale material? How does the physical change affect the thermodynamics?
Excellent question. Well, I can tell you there's a lot of theories about that. The sort of simplest one is that you increase the surface to volume ratio. So materials want to be in the bulk form. The surface is inherently less stable. So the more surface area you have, the less stable the material is. But it's likely much more complicated than that. It has to do with when you get down to the scale of a few nanometer diameter, you're looking at something that's not really a molecule, but it's not really the bulk either. And so its electronic structure is different from either one of those. And that's difficult to predict. We also know that the surface of those particles interacts with other reactive groups that are inside the pore, and you can actually cause charge to be transferred either to or from the hydride, and that causes some destabilization as well. So it's actually a really interesting chemistry question. Happy to talk to you about it more, but it gets a little involved.
Thanks, Mark. Now we have another question from Marco Zvanovic. From a fairly lay perspective, does this technology have promising application? For example, let me make sure I can read this.
Did you say from a thermoelectric perspective?
From a fairly lay perspective, does this technology have promising applications, for example, in situ H2 storage from a solar-driven electrolyzer?
Yeah, well, definitely. So I mentioned that we're starting to be much more comprehensive about looking at the hydrogen economy, and transportation is just one aspect of that. So there's lots of stationary applications where metal hydrides could be used. And for example, considering things like a microgrid or backup energy storage, metal hydrides could definitely be used for that. And that's a case where you don't really care so much about the gravimetric density, but you do care about how much of the volume that you have, and you care about not having to do something like cryogenic storage. So those kinds of applications are now starting to be looked at much more closely than they have in the past.
Okay. Another question from Claire Becker-Castle. Realistically, when would a commercial vehicle be available in the marketplace?
Using this material?
Using this material.
Well, historically, it takes about 20 years to get a material out of the laboratory and into a commercial market space. And that's true of almost anything. It's true of Velcro. So we've been working on this for probably about 5 years. There's a huge impetus to push these technologies forward and get them to larger scales and higher TRL. I'm ever an optimist. I would say it's possible that we could have a demonstration vehicle within 10 years. I think it's very likely, actually, we could have a demonstration tank that's independent of the entire vehicle within 5 years. And my colleague Vitaly Stavrile has been standing here to help out. He has a response also.
Yeah, so I want to time in here. So there are actually, as Mark mentioned earlier, there are forklifts that already have metal hydrides. Where we're looking at applications where obviously the light duty vehicles is the most challenging application. The going up in weight, these heavy duty vehicles, that could be a application that could be more amenable for metal hydrides because they're still heavy. But for in principle, the technology is here. For forklifts, there are already forklifts operating on metal hydrides in conjunction with the fuel cell. And the next step is probably heavy duty vehicles, and that's probably realistic in the next decade.
Yeah, and I think it's good to point out here also that the reason we're focusing so much on volumetric capacity and not gravimetric is that there's a finite amount of space available on a Class 8 truck to store hydrogen. And if you allow that to flow over into, let's say, the trailer, now you're impacting the amount of the capacity, the cargo carrying capacity. So you want to minimize that as much as possible. Interestingly, we've been looking at other applications like rail, and it turns out that for locomotives, they actually want more weight because that gives them better traction on the rails. So this could be another possibility for using a metal hydride.
Thanks, Mark. Thanks, Vitaly. Definitely good response. Another question came in from Melanie Davidson. If we are able to figure out materials-based storage of hydrogen at low pressure, what would that mean for hydrogen transportation vehicles? It sounds like it is tackling weight, cost, and energy efficiency. Is that correct? And how does it affect future design of fueling systems?
Yeah, so excellent question. Yes, it would definitely affect all of those. One thing that is not listed there is that if we could have a materials-based system that stores hydrogen at 100 bar or less, that gives the vehicle manufacturer much more flexibility to design the fueling system. When you're operating at 700 bar, you're pretty much restricted to making a tank that looks like a cigar with spherical ends on it. But if you can go to lower pressures than that, you can now have more flexibility to shape that tank. If you look at your gasoline tank sometime in your car, you'll see that it's not a uniform shape, but you could never store 700 bar hydrogen, something like that. So an impact of this would be, I think, to lower the cost of hydrogen fuel cell vehicles because the cost of the tank would go down. It should make the fuel cheaper because you will not have to invest so much in building a fueling station. The compressors for 700 bar are much more expensive than they are for 100 bar. So we should be seeing reductions in cost across the board.
I would add here that in addition to the cost of the compressor, kind of the upfront cost they need to invest in the infrastructure for 700 bar or 350 bar, there's just the pure from the energy efficiency standpoint. It takes a lot of energy to compress hydrogen gas, and I think the math is you use about 10% of the total energy of hydrogen to compress hydrogen to 350 bar, and it's 16 or 17% to get all the way to 700 bar. So that could yield some significant energy savings and cost savings ultimately.
Yeah, exactly.
That's a good point. I was just going to bring that up. There's definitely some energy efficiency savings compressing it down to 100 bar, 350 bar versus 700 bar. I guess this is a good follow-up question from John Baptiste Gallo. Can you describe how such a system would be installed on a Class 8 truck? What would be needed to make it work given the high operating temperature?
Yeah. Well, unlike a light-duty vehicle, there could be more than one tank. So if you have more than one tank, then the amount of storage material in there that has to be heated is lower. So that improves the thermal balance. 250 C, we think that's a bit high. As I said, we're trying to shoot for 200. The metals can take it. So it would be a matter of putting some efficient insulation around that. Obviously, you don't want a metal tank at 200 degrees C just sitting there. But I'm not a mechanical engineer, but I think I can be persuaded that that's achievable without having a major impact on the vehicle weight.
Yeah, and on the practical level, I would add here, on a practical level is that heat, the energy that you need to heat up the bed would have to come from the hydrogen that you already store on board. So you would sacrifice some of the hydrogen would go to heat up the bed to the optimum temperature. Ideally, as I think Mark indicated earlier, ideally we would want a system that operates at 80, 85 degrees C. In that case, you just recycle the heat that generates from the fuel cell. So that's a straightforward way to increase efficiency. It may be hard for a metal hydride, but that's I think in some sense that's sort of the system, the ideal system that we'd want to have for a metal hydride.
Yeah, and it's worth noting that the limitation, this 80 degrees C, that limitation comes from the fact that a PEM fuel cell, proton, polymer fuel cell, that membrane has a lot of water in it in order to increase the rates of proton transfer. And so if you could make these membranes out of something that could stand higher temperature, that would be a big help towards materials-based storage. And there are demonstrations of proton transporting membranes at temperatures as high as 150 degrees C. So personally, I think we have to come at this problem from both ends. We need to make the fuel cell capable of operating at a higher temperature, and we need to reduce the temperature that we have to operate the storage system.
Sounds like a project we can work on after this one, right?
Yeah, exactly.
I want to be conscious of time. I know we're 2 minutes after, but this is the last question from Carlo Andrew Trinidad. If we are considering the operating temperature of the storage, does that affect the desorption of hydrogen gas using the metal hydride with nanocarbon?
Can you say that again?
If we consider the operating temperature of the storage, does that affect the desorption of hydrogen gas using the metal hydride with the nanocarbon? I'm trying to see if Carlo is on. If he's on, if you don't mind raising your hand and maybe asking that question in person.
While we wait, Michael, I can address. I think there are two aspects here. So there is the heat management aspect. You always need heat to get the hydrogen off the hydride bath. But then that's only half of the problem. And I'm not sure if the question is, obviously the hydrogen that comes off the hydride bed is going to be warm. It's going to be hot, right? But with the balance of plant, that will have to be addressed so that the hydrogen is delivered to the fuel cell at the right temperature.
Is he perhaps talking about refueling? I mean, it sounded like the question had to do with the desorption. So, yes, I think if I understood the question, you need to heat the entire bed.
Carlo, can you raise your hand so I can unmute you? Maybe you can clarify the question a little bit. I don't know if you have that option of raising your hand. Okay, let me try and do this. I don't know if I can unmute you. Okay, well, maybe, I want to be conscious of time. It's 4 minutes after. I think we had a great discussion and great questions, and I can't seem to unmute Carlo. So maybe we can follow up with him afterwards. And maybe clarify, just answer it through the email. But if anyone who joined the presentation is still on, if you have any questions, feel free to email me, Vitaly and Mark after the webinar if you have any questions. And Carlo, we'll reach out to you. Maybe we can have a side conversation and clarify your question a little bit more so you can get the right answer. But I think that would, we're 5 minutes after now. I think that is the end of the presentation. So Mark and Vitaly, want to thank you both so much for taking the time to present on this topic, and look forward to the results.
Great. Well, thank you very much for giving us this opportunity. We really enjoyed it, and we appreciate the really excellent questions from the audience.
Definitely. And just a reminder, this webinar is being recorded and will be available on the SoCalGas Research and Development and Demonstration website and LinkedIn. So and we will send out information on follow-up. So look out for that in your email and on our website. Thank you, everyone. Have a good day.
Thank you.